So what exactly is the photoelectric effect? The photoelectric effect, just like the thermionic effect, is the emission of electrons. Although unlike the thermionic effect, the photoelectric effect is the emission of electrons due to exposure to radiation such as light. In thermionic emission, which we'll talk about later, it's the emission of electrons from a metal surface when exposed to high temperature. So in this case, there's radiation that's knocking onto this metal bar, and then electrons are streaming out. So this led scientists to wonder if it's possible that light can also have matter properties. Because imagine light, which was considered to be nothing but energy, knocking out electrons from this surface. So some scientists thought that if this were possible, then it means light contained some particles that could knock onto these particles to instill into them some momentum which made them possess this certain velocity, which was an interesting discovery, and it was a series of interesting experiments. Light stimulates the emission of electrons from the surface of a metal, which is the photoelectric effect. Below a certain frequency known as the threshold frequency, there will not be any emission of electrons. So there's something we need to have called the threshold frequency, or the starting frequency. Anything below the starting frequency will not stimulate the emission of electrons. Remember, we said in the previous videos that energy is quantized. This was where the theory came from. Okay, so it can't be, according to the example I gave, it can't be half a certain frequency, because if it were half, there will be no stimulation of emission for the electrons on the metal surface. And then this is true regardless of the light intensity. When the frequency of light is low, no matter how bright it is, with low frequency it can't emit electrons. But above a certain frequency known as threshold frequency, above this limit right here, there's going to be an emission of electrons from the metal surface, which increases with light intensity. So the brighter it becomes, the more light intensity you put into it with frequency above the threshold frequency, then you emit electrons. And the kinetic energy of those electrons, as you can notice here, the kinetic energy of these electrons would increase due to the difference between the energy you have in here and the threshold energy. We call it the threshold energy because remember from the previous videos we discussed that energy is equal to Planck's constant times nu, which is the frequency of radiation. So if we are using a nu sub naught as our frequency, then what we'll have as our energy will be energy sub naught, which is the threshold energy. Now the difference between the threshold energy and the energy that we actually have will be instilled into the electrons as kinetic energy. So the excess energy is transferred to the electron as kinetic energy, which we're just from saying, because energy has to be conserved, the energy that will be in excess will be instilled into electrons as kinetic energy, which allows them to be emitted from the metal surface. Now energy has mass, according to the previous video again, where a lot of scientists were interested in finding the relationship between matter and energy, and Einstein, Sir Albert Einstein, said there is definitely a relationship between energy and mass, in such that energy is equal to the mass times the speed of light square, which we can rearrange for mass and say the mass of energy is equal to the energy itself divided by the speed of light square. So in such a scenario, we can say, knowing that the energy of a photon is equal to Planck's constant times speed of light divided by lambda, we can substitute this value in there. If energy is equal to this, then we can remove energy and replace it with its actual value, which is hc divided by lambda, and this gives us an interesting equation that we'll be using more often in our calculations as well. This helps us to determine the mass of a photon, or the mass of light. Okay, remember, light is made up of a stream of photons. So when we are saying we are calculating the mass of a photon, it basically means the mass of light, which seems impossible, but true. Light has mass. Okay, now the fact that light has mass and it's a wave led scientists to develop this term right here. So light is said to have dual nature. Okay, the property of light having both mass and wave properties is called the dual nature of light. In other books you find it's called the duality of light, which is the same thing, because it's got both properties of mass and waves, which it wasn't predicted to have earlier. After the famous relativity equation by Albert Einstein, there is a French scientist who emerged and said, okay, if light has got matter properties, does matter also have wave properties? This scientist was known as Louis de Broglie, and he proved it true actually. The result was that matter also has wave properties, although most times actually very insignificant because of the large particles. Say for example, does your book have wave properties? Does it have frequency, and does it have wavelength? Seems to not make sense, does it? But well, actually they do have wave properties, just that we can't notice them because wavelength and mass are inversely proportional. So the larger an object, the smaller its wave properties. Here is an interesting example that we'll consider today, which says compare the wavelength for an electron of mass 9.11 times 10 to the negative 31st kilograms and traveling at a speed of this much, 1.00 times 10 to the 7th. So we're comparing the wavelength for this electron to the wavelength for this ball. Okay, we want to see how their wavelengths are related, if they are, or how different they are. It's pretty much of a plug and chug thing. Remember, the formula is mass equals Planck's constant divided by lambda multiplied by nu, which is what we derived in the previous slides. One might be tempted easily to use speed of light for the electron, because probably, I don't know if it's more, that's why people tend to make this mistake, but it's very common actually. So an electron is matter, it's not a wave. Okay, so they've given us the speed of the electron, which is here. There's no need to use the speed of light. Okay, so what we do is pretty much substitute in the values. We know this is a constant, the mass has been given, the velocity has been given, so the wavelength is 7.27 times 10 to the negative 11th power meters. Okay, so notice the order of magnitude for the wavelength of the electron. It's 10 to the negative 11th. How about for the bow? Well, for the bow, we have, substituting in everything, turns out to be 1.89 times 10 to the negative 34th meter. Now this value is way smaller than this value. the wrong symbol. This value is smaller than this one. And like I said, wavelength and mass are inversely proportional. So the bigger an object, the smaller its wavelength is. That's why you can't notice your own wavelength, but experimentally you can find the wavelength of a stream of water waves. Okay, so thank you very much for watching. If you haven't subscribed, consider subscribing, invite your friends to like, and stay tuned. Thank you very much for watching. Have a great day.